Predict the next 10 seconds of a river for me.
The water.
Every ripple, every leaf coming down the current, exactly where each one lands. Go.
I can't. Nobody can. That's just noise.
Right. So here's a guy who says, that's the whole mistake. We built AI to predict the next thing, the next word, the next frame, and then we act shocked when it wastes itself trying to predict the ripples.
This is LeCun.
This is LeCun. Yann LeCun, one of the people who started this entire era of AI, and for 3 years he's been saying the era took the wrong road.
The language models are an off-ramp line.
That one. And his fix has a name, and it basically comes down to, stop predicting the picture, predict the idea of the picture.
Which is a slogan until somebody makes it work.
And that's the episode. Because somebody did. On images, then video, then an actual robot. And then this past winter they stopped tuning it and finally proved it. And right around then he walked out of Meta to bet a startup on it.
So either we're watching a founder of the field call the top, or talk himself off it. And I genuinely don't know which yet.
Neither do I. Let's find out. New here? This is Breach Protocol. We crack open the AI research everyone's passing around and tell you what's actually inside. The result, not the demo reel.
I'm Vestra. I go after the mechanism, how a thing works, and whether it survives a hard look. Luna brings the big idea. I check whether it holds.
And I'm Luna. I track the thread across papers. Today's different though. One idea, start to finish. Not 12 papers, one architecture, and the 4 years of work it took to make it real.
It's called JEPA. Stands for Joint-Embedding Predictive Architecture. It's Yann LeCun's bet on what a machine that actually understands the world would have to be built like.
And the whole field right now is racing the other way. Generate text, generate video, generate whole worlds you can walk through. He says that's the off-ramp.
So we follow his road instead. All the way to the part where he quits to go build it. And I'm gonna lean on every step, because the elegant ideas are exactly the ones that need it.
Let's get into it. Start with a question he opens with. A teenager learns to drive in about 20 hours. Behind the wheel, 20 hours and they can basically do it.
And a self-driving stack eats millions of miles and still gets surprised by a plastic bag.
So what does the teenager have that the machine doesn't?
A model of the world. They already know cars don't teleport, that a thing behind a truck is still there, that wet road is slippery. They're not learning to drive from scratch. They're bolting driving onto a world they've understood since they were 2.
He's got this line, that no AI today has the common sense of a house cat, and he means it as plumbing, not as an insult. The cat has a working model of how things fall and roll and hide. The chatbot has read about it.
Fine, but that's the easy version of the critique. Everyone nods along at models lack common sense. What's the actual technical claim?
The technical claim is about what you train it to predict. Take a model, make it predict the future, the next frame of video. To be graded right, it has to predict every pixel.
And most pixels are unpredictable. The leaves, the ripples, the exact grain of the carpet.
So it burns its whole brain trying to nail noise and gets punished for missing the unmissable. Picture a car coming up to a fork in the road.
Goes left or right and you can't know which.
You can't. So a pixel predictor tries to draw both futures at once and smears them into mush. But the thing you actually care about is one bit, left or right. Everything else, the trees by the road, the cracks in the sidewalk, throw it out.
And that's the move, isn't it? Don't predict the world. Predict a stripped-down description of the world, where the only things left are the things you could actually have predicted.
Predict the idea, not the picture.
Okay, I'll grant it's a clean idea, but here's where I get suspicious. Throw away the unpredictable stuff is doing enormous work in that sentence. Who decides what's unpredictable? If the model invents the description and the model decides what to keep,
then it can cheat.
Spectacularly. And that's not a footnote, that's the whole game. Hold that thought, because it's the trap the next 20 years of this idea spend fighting.
So, lay out the trap.
Here's the setup. You've got the present and a possible future. You run each one through an encoder, a thing that turns it into a list of numbers, a description, and you train them so the present's numbers can predict the future's numbers. So they agree.
Agree in the stripped down space, not pixels, descriptions.
Right. Now, what is the single laziest way to make two descriptions always agree?
Make them the same.
Make them identical no matter what you feed in. Map every image, every video, everything to the same numbers. All zeros. The prediction is now perfect forever because everything predicts the same constant. And the model has learned absolutely nothing about the world.
That's collapse.
That's collapse. And it's not some rare glitch, it's the best possible score. The model slides into it like water finding the drain. There's a paper this year that just states it flatly as a theorem. The easiest way to win this game is to learn nothing.
So how do you stop it?
For years. Tricks. The main one, you keep a second copy of the model, a teacher that moves slowly. The student chases the teacher's answers, and because the teacher lags behind, the two of them can't dive to zero together.
A moving target so it can't just sit down.
Roughly. And it works. That's the uncomfortable part. It works, and for a long time nobody could really say why it was the right thing, or when it might quietly stop working.
It's a folk remedy.
It's a folk remedy, and honestly, the JEPA story for years is a stack of folk remedies that all work. Right up until somebody in 2025 asks the one question that makes every single one of them unnecessary. But we have to earn that. First, does the basic idea even do anything? Images.
First real version, still images. They call it I-JEPA, I for image.
The simplest possible test of the whole philosophy.
You take an image, hide most of it, and show the model one chunk that's left. Its job, predict what's in the hidden parts, but not the pixels of the hidden parts.
The description, the representation.
You run the full image through that slow teacher to get the true description of the hidden blocks. And the student has to predict that from the one visible chunk.
And here's the experiment I actually care about, because it's the one that could have killed the whole thing. They ran it both ways. Predict the description versus predict the actual pixels. Same model, same everything. Just swap what you're aiming at.
And?
Predicting pixels was far worse. Not a hair, the features you got out the other end were dramatically weaker. Same machine. The only difference was whether you asked it to paint or to understand. Understanding one, clean.
That's the moment the slogan becomes a result.
That's the moment I started taking it seriously, yeah.
And it's cheap. Getting there took something like 1/10 the computer power of the big paint the pixels back method everyone was using at the time.
Which tracks. You're not wasting effort rendering carpet you'll never need.
And one thing my brain loves here, it came out unusually good at the where of things, depth, counting, the spatial stuff.
Because the older trick, squint at two random crops of a photo and call them the same thing, throws location away on purpose. This didn't, so it kept a sense of space.
So is it just better, full stop?
No. And this is the honest asterisk that shadows the whole family. The win shows up when you freeze the model and use it as is. If you let yourself retrain the entire thing for one specific task, the old paint the pixels method roughly catches back up on the raw score. So it's not JEPA wins everything. It's JEPA. JEPA hands you a better starting point for free.
Free is the word that matters, because now you scale it, and you stop using photos. If your whole bet is learn the world by watching it, photos are a strange place to stop.
Photos don't move, the world moves.
So, video. Same trick, but now you hide a chunk that runs through time. A tube punched through the clip. Predict the description of what's behind it.
And here's what I want answered. Did it learn anything you genuinely cannot get from still pictures? Because if video training just gets you back to image level features, why bother?
They've got the perfect test for exactly that. There's a benchmark. Picture it as, here's a short clip. What's happening in it? And it's built so that the same clip played backwards is a different answer.
So you can't win by naming objects. A hand and a cup are a hand and a cup in both directions. You only win if you understood the motion.
Right. Appearance is useless on this one. Only motion counts. And here's the result. Image models. Ones that have seen basically the entire internet of pictures. On that test, they're near a coin flip.
A coin flip.
And a model that only ever watched video. No labels, nobody telling it what anything was, laps them.
Okay, that is the cleanest possible version of the point. Appearance and motion are two different kinds of knowing, and you simply cannot get the second one out of a photo album, no matter how enormous the album is.
That's it.
One thing though, same model on plain what object is this? Does it keep up?
It doesn't. It's noticeably worse at flat photo classification.
So, not a free lunch.
There, read. That's a diet problem, not a brain problem. The video it learned from just isn't as visually varied as the whole internet of images. Feed it richer video and the gap should close.
Plausible. And one honest caveat, because people overstate this constantly, this version did not learn physics. This paper showed motion features. That's it. The physics claims come later, and they come with a body attached.
Which is exactly where it goes next. You make it big, and you hand it a robot. V-JEPA 2, 2 moves, and they're the two that turn a nice features paper into an actual world model.
Go.
Move 1, scale, 1,000,000+ hours of video. And at that size, it starts to anticipate. Watch somebody in a kitchen and call the next thing they're about to reach for, seconds before they do.
Predicting forward. That's the first half of any world model. Guess what happens next?
Move 2 is the one that got me. They take that model, show it a little bit of robot video, and teach it a new skill. Given what you're seeing and an action you might take, predict the next description.
Predict the consequence of an action in the stripped-down space.
And once you can do that, you can plan. Watch. You hand it a photo of the goal. Here's what done looks like.
And it searches.
It imagines action after action in its head, checks which sequence lands it closest to that goal photo, does the first step, then looks again and replans.
Imagine, then act. That is, word for word, the loop LeCun's been drawing on whiteboards for a decade.
And the payoff? 2 robot arms, in 2 different labs the model was never trained in. No reward, no lab-specific practice. And it picks things up and puts them where the goal photo says.
Hold on, never trained in that lab. How zero is the zero here? Because that word gets abused.
Fair to interrogate. The understanding came from internet video. The action skill came from a small pile of generic robot clips. Not those arms, not those rooms. So it really is planning somewhere new.
That I'm impressed by. And because it's planning by thinking ahead in its own compressed description, it's fast. Way faster than the other way people do this, where you literally generate video of the future and stare at it.
Dozens of times faster, roughly. Don't paint the future, just think it.
So where's the catch? There's always a catch.
The catch is humbling. Same week, they put out physics tests. The violation kind, the ones you run on babies. Show 2 videos, one where something impossible happens, see if the model is surprised.
Object permanence again, ball behind the box.
People near perfect, infants near perfect, the best video models near a coin flip.
So it plans in a clean room and flunks the toddler test.
Both true at the same time.
Then say the honest version of it. It's a world model good enough to be genuinely useful, and nowhere near good enough to be done. And the reason the next paper exists is somebody looked at the whole stack of tricks holding this together, and got nervous.
This is the one, late last year, LeJEPA.
And this is the one that actually changed my mind, so let me set it up properly.
Please.
Remember the folk remedies. The slow teacher, stop this gradient, schedule that knob. Every JEPA was a careful balancing act of tricks to keep it from collapsing, and every new dataset you might have to retune the lot. Brittle, and nobody could prove any of it was actually right.
It worked, but no one knew why.
So Balestrio and LeCun ask a completely different question. Forget how to prevent collapse. Ask, what shape should the descriptions be? If you could pick the ideal arrangement of all those number lists in space, what is it?
And they don't guess. They prove it.
They prove it. And the answer is the most spread out, no favorite direction shape there is. A cloud of points with the same spread whichever way you turn it. The technical name is an isotropic Gaussian, but the picture is just an even, round cloud. No spikes, no flat sides.
Why that shape?
Because you don't know yet what you'll use the model for. If the cloud is stretched thin in some direction, then any future task that happens to care about that direction is starved. There's no detail left there. The even cloud is the one that's least bad at every possible future task. It's the fair shape.
And here's the part that made me laugh out loud.
The even round cloud is the exact opposite of collapse. Collapse is everything crushed onto a single point. A cloud spread evenly in every direction physically cannot be collapsed. So if you just require the healthy shape,
you never have to prevent the disease.
The whole problem dissolves. No slow teacher, no stop gradient, no schedules, none of it. You require the shape and collapse is off the table by construction.
Okay, but how do you require a shape in a space with hundreds of dimensions? That sounds impossible to even check.
This is the clever bit. You can't check the whole high-dimensional cloud directly, so you shine it through thousands of random one-dimensional slices. Like holding the cloud up to the light from 1,000 random angles and checking that every shadow is a plain bell curve. Get all the shadows right, and the whole cloud is right.
And that's cheap.
cheap, and it splits across machines, and it's one knob, after a decade of hand balancing 5 things at once.
Give people the scale of it. How well does it hold up?
That's the other shock. They run it across something like 60 different network designs, from small ones up to billion parameter monsters, and it just stays stable. Same recipe everywhere, no babysitting. And the whole thing is about 50 lines of code.
There's a bonus too, and it's quietly huge.
The training number tells you how good the model is going to be. Normally, you have to go test a model on some labeled task to find out if it's any good. Here, the training signal alone predicts it. You can pick your best model without any labels at all.
So put it together, what did this paper actually do?
It took the messiest, most hand-tuned part of LeCun's entire program and replaced it with one proof and one knob. There'd been a paper the year before, I-JEPA, that spotted the cracks and patched them by borrowing a trick from the rival camp. This isn't a patch. This is rederive the thing from scratch so the crack can't even form.
And reportedly, it's the last big thing he did at Meta before he left.
Which, knowing it's the capstone, lands differently. He didn't leave on a demo. He left on a proof.
And then this spring, they cashed the proof in LeWorldModel.
This is the proof from the last segment plugged straight into a world model.
Right, and it does the thing none of the others could do cleanly. It learns a world model straight from raw pixels, end to end, with just 2 ingredients. Predict the next description. Keep the cloud healthy. That's the entire recipe.
No slow teacher, because last segment it doesn't need one anymore.
And it's tiny. We're talking one little number list per frame, a model small enough to train on a single graphics card in an afternoon.
Hang on, that's almost suspiciously small. The video world models people make headlines with are gigantic.
And this one plans dozens of times faster than those on the control tasks, because it's thinking in that tiny compressed space instead of generating pictures.
Okay, but small and fast isn't the same as understands. Did it actually learn structure, or is it just very efficient at nothing?
Here's the detail that ends the episode for me. Nobody taught it physics. But you can measure how surprised it is when its own prediction turns out wrong. And when you make an object teleport, just vanish and pop up somewhere it physically couldn't be.
It gets more surprised than if you just recolored it.
More surprised by the impossible thing than by the harmless thing. With 0 physics lessons, it fell out of 2 things, requiring the healthy shape and predicting forward.
That's the exact thing the whole field has been chasing on those baby physics tests. And here, a model you could train on a gaming PC shows a flicker of it for free.
A flicker, not solved.
A flicker. But it's the right flicker in the smallest possible system, which is precisely where you want to catch it. If it only showed up at billion parameter scale, you'd suspect it just memorized a lot of falling objects. At this size, you can't tell that story. There's nothing to memorize with.
Same month, by the way, they also fixed the knows what, not where weakness in the big video model. Sharper depth, better grip on objects. The program's moving fast.
It is, which is the perfect moment to ask the rude question. Is any of this actually the path? Or is it a beautiful idea that wins on tidy little tasks? Let me make the strongest case against this properly. There's a paper from this past summer, Critiques of World Models, and I'll be upfront about its angle. The authors are building the rival, the generative kind. So they're not neutral, but the arguments are real.
Give me the hardest one.
The hardest one is that non-generative is partly a marketing word. The whole pitch is, we don't generate, we just predict in description space. But when you actually plan, you roll that prediction forward, step after step, feeding its own output back in. That's the same forward-generating loop you claimed you were escaping. You're just not printing the pictures.
So the thing it said, it avoided.
It's doing a version of it, quietly. Next one, most of the wins are still in controlled settings. A clean tabletop, a driving dataset. Their line is basically, show me make break fast, not pick up the cup. The long, messy, real-world tasks are still mostly unproven.
And the deepest one?
The deepest one should keep them up at night. Everything is judged inside the model's own invented space. So how do you ever know it learned the real world, versus quietly found a clever way to look consistent to itself? With pixels, reality checks your work. The picture's wrong or it isn't. In pure description space, there's no outside referee. They call it the grounding problem.
Okay, I'm not going to fully concede though.
Go.
2 of those 3, LeJEPA actually answers. The anti-collapse tricks are brittle. That was true, and it's the exact thing they just replaced with a proof. And you can't tell understanding from collapsing. The whole point of requiring the healthy cloud is that collapse is off the table. So that ambiguity shrinks. Hard.
That's fair on the brittleness. The grounding worry, I don't think a proof fully kills. But yeah, it's weaker than it was a year ago.
and on its all toy tasks. A robot picking things up in a lab it's never seen is not nothing. Neither is getting surprised by teleportation with no physics lessons.
No, it's not nothing. Here's where I land. The critique lands clean punches on the old version of this story. The 2025 and 2026 work moved the target out from under it. It is not proven. Make Breakfast is genuinely unsolved. But the It's Just Hacks and Toy Problems read is about a year out of date.
So a real disagreement, not a winner.
Not yet, which is the honest place to be standing.
Pull all the way back. Why does this fight matter to anyone who isn't training models for a living?
Because all the money is on the other side. The whole industry right now is pouring billions into generating worlds, video you can watch, environments you can walk through, and it is genuinely impressive. Today. Right now.
And JEPA is the standing bet that watchable isn't the same as understood, that a model graded on how pretty its frame looks is optimizing the wrong thing, and that real understanding shows up somewhere else entirely.
As a robot that can plan toward a goal it was never trained on, not as a nicer looking picture.
And here's the human turn. The person who's been arguing this, Yann LeCun, helped invent the technology this entire era is built on. The networks underneath basically all of computer vision decades ago, that's substantially him.
And late last year, he left Meta. After a rough flagship launch, new leadership brought in over the lab, layoffs. He walked to start a company built entirely on this idea.
So you've got a founder of the field saying the field is on an off-ramp, and putting a company where his mouth is.
And the timing is not an accident. He didn't leave on a vibe, he left right after the proof. The idea finally had a spine under it, and that's the moment he bet his next decade on it.
So the honest scorecard.
It is not a finished answer. Generative video isn't going away, and it might even turn out you need both kinds. But this is the most worked out alternative anyone has put on the table to just scale it up. It has a proof now, it has a robot, and it has a startup.
An idea, a body, and a bet.
Which is a lot more than it had a year ago.
So that's the arc. Start with a complaint, stop predicting pixels, turn it into an image trick, then a video model, then a robot that plans, and then finally, prove the part everyone had been hand-tuning for years.
And stay honest about the whole. Nobody's shown the scales to the long, messy, real-world tasks yet. The clean room is not the kitchen.
What are you watching for next?
Whether it gets out of the clean room. One real, long task in the wild. Make the breakfast, not lift the cup. Done by planning, not by scripting. That's the milestone that would settle it.
I'm watching the startup. Whether predict the idea, not the picture ships as something you can actually build on, or stays a beautiful paper.
Either way, it's the most interesting bet in AI that isn't just a bigger model.
This has been Breach Protocol. We cracked the black box, so you don't have to.
See you next time.